Section 3.4 is exponential growth and decay. So this is a nice application in the course. Typically, we just do a lot of abstract looking math problems. And this is finally a place where we can connect some of the concepts of derivatives to real applications or math modeling applications. So exponential growth is typically the type of growth that a population of people or bacteria or any living organism might exhibit. And exponential decay is the type of decay that half-life might exhibit, the half-life of a chemical isotope, or anything else that sort of decays in value or decays in quantity. So I think one kind of practical example that's interesting is maybe the value of a car. An automobile tends to depreciate over time, and it's reasonable to model that growth as an exponential decay or as an exponential decline in value. A linear decline in value would be problematic because at some point the line would cross the x-axis, and if the line crosses the x-axis, then that value of the car is 0, and it's going to go under the x-axis, and that means we have a negative value for a car, which is somewhat problematic. You'd think that a car inherently has some kind of value, at least for the raw material. So that's really just a matter of this asymptotic behavior here, or exponential decay, or on the other hand, exponential growth, moving left to right on the time axis down here. So that's kind of what this is all about. So anyway, to get into the actual details of it, we're going to treat y of t. Y is a function of t, and y is some quantity. It could be the number of individuals or cells in a population, or members of a population. T will pretty much universally be time, lowercase t at least. And then we'll talk about the rate of change of y with respect to t. And, we're going to assume that the rate of change of y with respect to t is actually proportional to the value y of t. So this would be something like saying that the rate of change of a population is based on, well, how many individuals are already in that population. So if we look down here and look at this equation, dy dt, the rate of change of y with respect to t, or the derivative of y with respect to t, if it's equal to k times y, well, k is just some constant, and we'll just say it's that for now. What we're saying is that the change in the population over time is proportional to the population itself. This is probably best seen if you think about, an epidemiology example. Maybe we have an infectious disease that we're noting, and maybe y, or that we're observing, and maybe y is the number of people who are infected, right? The population of infected individuals. If the number y is greater, if we have more infected individuals, then it should make sense that our rate of transmission, the rate at which we get more infected individuals, in other words, spread the disease around, is going to be higher, right? So that's how we have that exponential growth that epidemics tend to exhibit. So, in a lower count of people, fewer people in this, fewer values for this value y would indicate a lower rate of transmission, right? Or a lower change rate because there are fewer people to get the rest of the healthy population sick. So I think we can kind of see the sense in that. Now, what is k, right? That's the question we can think about in this situation. If we solve for k in this equation, we can get a decent look at that. K is equal to the rate of change of y with respect to t divided by y. So we've divided by the total count in the population at that current time. And what that is, it's a relative growth rate, right? It's the rate of growth, rate of change in the y variable relative to the amount of members in the population, or the quantity of y, whatever this quantity might measure. So k is the relative growth rate. And as is, that keyword relative there tells us that we can really think of k as a percentage, right? It's a percentage by which the population is increasing in any given instant, okay? So k in all of our problems will be constant, right? And that's a reasonable assumption. in an infectious disease that has something to do with the transmissibility of the disease, right? A larger value of K means, we're going to get larger values for our rate of change of Y, means we're going to be a more infectious disease, right? So a higher relative growth rate leads to more infections, more cases of infection. Or similarly, for a relative growth rate like that, if this was something like an interest rate, then that means that the account is going to grow that much faster. So a lot of things are modeled by this rate of change equals to being equal to the or being proportional to the amount of it, or the quantity or the amount of individuals in the population. So that's a big clunky sort of introduction to all of this. Now, this thing here is technically a differential equation. Okay, so this is kind of beyond Calc 1. However, we don't need the tactics of solving a differential equation. We're just going to be given that solution. Okay, so here, the directions in this say to determine a function that satisfies this equation. Well, with a little bit of guess and checking, I think it's feasible that a student might come up with this. But then again, a Calc 1 student is not required to. Here it is. Here's one function that does this, that satisfies this, right? If the function y is equal to e to the kt, then if I take the derivative of this function with respect to t, right, both sides of this equation right here, I get dy dt on the left, and on the right, I just have to be careful to take the chain rule. The derivative of e to the kt is e to the kt times the derivative of kt. So when we carry that out, well, the derivative with respect to t of kt is just k. So we have k times e to the kt. And it's at this line right here that we realize, well, e to the kt is equal to y. So I can substitute y in for this, e to the kt, and I have dy dt is equal to k times y. So what we've just proven, or just checked, is that if y is equal to e to the kt, well then dy dt equals k times y. So we've confirmed that this function is a solution to this differential equation. And that's the key thing, right? So we impose this equation to model the behavior of a population or quantity based on certain physical properties or observations about it. And then we solve that equation to get this function here. Of course, we didn't show really how you go about solving that, but nonetheless, we have the solution, and we use this solution to actually model the population growth going forward, or the quantity growth, or quantity decay, if it's half-life or some kind of declining quantity. So we can do better than this, though, and that's the bad news. We can generalize this a little further. If there was a constant times e to the kt, then this would still work, right? So if we let c be some real number, some fixed arbitrary constant, and we let y be equal to c times e to the kt, we take this derivative again, ddt of both sides of this equation. We get y prime, or dy dt on the left. And here, by the derivative e to the kt, so this survives. C just exists as a multiple by the constant multiple rule, and this multiple of k comes out of the chain rule for the derivative with respect to t of kt. And what we see now is we have another copy of y after we've taken that derivative with a multiple of k times it. So then y prime is equal to k times y. Again, that satisfies the differential equation. So we can go one more step to kind of finalize this solution to this differential equation, this function that we're going to use commonly, and figure out, well, what is the value of c? Can we get a handle on what that is? And we can. We can do y of 0, because we know that e to the 0 is 1. So we'll do that. Y of 0 in this given equation here is going to give us c times e to the k times 0. Well, that's c times e to the 0. E to the 0 is 1. So we just end up with a c. So again, students don't have to come up with this. This is just everything is called an initial condition. Y of 0 is equal to some value, right? But if we know what our population is when we start the whole experiment, or whatever it is, or the observation we're looking at, then we know what value to put here for this function. So in general, And we don't need to do much of that as students. Maybe if you can understand the bulk of that, that's great. You can see where this function comes from as a solution to this differential equation. We come down here and realize that we're going to deal with this formula right here as a modeling formula. And most likely you've seen this in a college algebra course before, where you talked about a population model where P sub 0 is P naught, and that's the initial population. And we have e to the kt, and k even back then was referred to as the relative growth rate. So some percentage by which the population grows instantaneously or declines, whatever it might be. If k is negative, it's decline. If k is positive, it's growth. So there we are, and generally we'll just use y variables, but swapping out for p is just as well. This might even look like a continuously compounded interest problem as well, right? Now the only difference is k would be an r instead, and that r would be an annual interest rate. And p naught would be the principal, the initial amount of money that we invest in the account, and t would be the time in years that the money is invested, and we could find any future amount where based on however many years have gone by t, we can find that future amount as a function of t. So hopefully those are some connections to some familiar places. But if not, I think this should be somewhat familiar to most college algebra students, so we'll get to work on this. So what I've done here is I see that I'm going to work with an exponential modeling problem. So I wrote down two things that I might need. Primarily, I'm going to need this bottom one, the solution to that differential equation, right? But there's one question where I'll need the derivative, right, or the differential equation itself. Okay, so remember that t is equal to time, whatever units time is measured in. As long as we're consistent, we'll just stick with that. Y is the population of something, and in this case, we're talking about, we have, in a nutrient broth, each cell of E. coli divides into 2 cells every 20 minutes. The initial population of a culture is 60 cells. Okay, so they ask us to find the relative growth rate. So we need to get started on this. In other words, find K. Okay, well, our initial population, there's a key word there, is 60 cells. So Y of 0 is 60, right? So here we go. Y of 0 is equal to 60. At time t equals 0, Y is 60. That's how we read this, Y of 0 equals 60. So now I know I can update my general equation to make it more specific or customized to this problem, and I'll write it as this. So I've replaced y of 0 with 60, e to the kt. Ultimately, I'd like to know this whole formula so I can model the population for future times t, so I'll need to know what k is. So this is really just the first step to doing that. So the information we haven't used yet is the fact that each cell divides into 2 cells every 20 minutes. So at time 0, there are 60 cells. At time t equals 20 minutes after this experiment or observation has started, we should have 120 cells, double 60, right? So at y of 20, we have 120, 2 times 60. Okay, so that's the key step to this part, and the rest of this is just algebra. So what I know then is that 120 is equal to y of 20. Well, this formula tells me that y of 20 is 60 times e to the k times 20. And there I've written that down here. And now when I look at the far left-hand side and the far right side of this equation, I have an equation in k. The only unknown in this is k. Right? So I just need to solve for k. So I'll divide by, so I'll write it down, right? 120 equals 60k, e to the 20k. Divide by 60 to get this line. Take the natural log of both sides to cancel the exponential function. Be sure when you take the natural log that you just have the base E exponential function here. We can't do it at this step because that's not a clean application of natural log to the exponential function E. It's got to be isolated like this, as highlighted, before we can do that. And then we get a nice cancellation. Natural log of 2 is equal to 20k. Only the exponent survives when we take the natural log of the right-hand side. So solving for k, I just divide by 20. So k is equal to the natural log of 2 over 20. And this is the most useful way to write this. It's the exact form, right? It's the most accurate form. Just for interest's sake, I wrote this as a decimal or as an approximate decimal, and then I converted it to a percentage just to see just to get an idea of what K is. Well, the first thing I see is that K is a positive number. And that's good because this thing is growing, right? We're getting more cells. Our relative growth rate should be positive. If the population was shrinking, we'd expect K to be negative. So that matches. And then it's not a crazy value either, right? Looks like K is growing by 3.4%, at any given instant, right? That's the rate of growth of this population. So anyway, that's neat to see, but we're going to use this number in our actual formula. Part B says find an expression for the number of cells after T hours. So this is our general model, right? So this is saying that the population Y for any given time T can be calculated by this function right here. You just plug in that time for T. And all we had to do to build this was remember what our general model looks like, our exponential growth model or decay model. And we just had to fill in for K, and we found Y naught or Y of 0, and we've got everything we need, right? Now, if we predict with this, we just need to plug in times for T. And that's what part C asks us to do. Find the number of cells after 8 hours. Well, 8 hours, remember our time was in minutes. So we have to be careful here. We have to convert hours to minutes. Don't put the wrong unit of time in here. Once you set this model up, this model takes time in minutes, not hours. We could have calculated it in terms of hours, but that would have meant that Y of 20 minutes would have been Y of 1/3 hours, right? And we'd have to do all these adjustments to how we came up with K in that case. We'd have to change those values. Anyway, it's easier to change hours to minutes at this point. So here's us doing that. We have 480 minutes. That makes up 8 hours. Now Y of 480, so the population or the number of cells after 480 minutes is 60 e to the natural log of 2 over 20 times that T value of 480. And that comes out to, I don't know, I've simplified some things, right? 480 over 20 looks like it came out to 24 times the natural log of 2 here. And on an exam, of course, I'm pretty easy about this. If you don't have a calculator, I think I'm fine with this. Incidentally, I used a log law to move 24 to the exponent of 2, and that means I can cancel e and natural log here. That's just an interesting fact. And when I do that, I get 60 times 2 to the 24th. None of that is important. You could box this up in an exam unless I'm asking you to express it to a certain decimal amount or something like that. In this case, this comes out to this much. 1,006,632,960 cells at the 8-hour mark. Okay, so in exponential growth indeed, right? So find the growth rate after 8 hours. Now let's keep this in mind. They're not asking for the relative growth rate, they're asking for the growth rate. The growth rate is dy dt. Right? It's the actual rate of growth of the change of the y variable with respect to time at a given instant. And this is at the 8-hour mark or the 480-minute mark. Now this is where I need this equation. So I need to know a couple things. Well, I need to know K. Well, I already know that, so that's good. I need to know Y of T for that given time, 480. Well, I also know that. 480, Y of 480 is what we found in the previous part. So I got everything I need. So dy dt at time t equals 480, or in other words, write it as y prime of 480 is equal to k times y of 480. Again, I'm just using this formula up here as is. And k is natural log 2 over 20. And y of 480 is the value I calculated over here. So I'll write that together. Now, I didn't put this into a calculator and come out to some value. That's fine. I box this up, of course, on an exam. If I don't ask you to round a certain number of cells or something, or express it as a fully approximated decimal, fully expanded approximated decimal, then no big deal. But of course, you could plug this into a calculator and see what you get. Note that natural log of 2 is a number that's less than 1. So that's going to make this number smaller. And we're going to divide everything by 20. That's going to make this number smaller. And that's what we would expect, right? The rate of change with respect to time at this instant should be less than the population, but it should be proportional to it, right? That would make sense. These cells we can't have 1 billion cells and replicate and have, 2 billion cells on the way in our replication, right? In addition to our initial 1 billion. Only each cell can be replicated. So anyway, that's just doing some answer sense sort of checking. Okay, part E, when will the population reach 20,000 cells? So this is a bit of an inverse question. When says I'm looking for a time t, right? And I'm going to go back then, and I'm asking about when the population reaches 20 cells, that's my y value. So I'm going to use this model that we put together, and I'm going to solve for t when I say that y of t is equal to 20,000. So here I swap out that 20,000, and the right-hand side just looks like the rest of my model. And it's an equation now in t. It's very similar to the work we did to solve for k. We divide by 60 on both sides. We get something like this on the left. I'm ready to take the natural log of both sides to cancel that exponential function, that natural e. So I have natural log of 1,000 over 3. Again, that's just this number simplified. And then the e's cancel with the natural log, and I have natural log 2 over 20t on the floor now. I solve for t by multiplying both sides by 20 over natural log of 2. And here's my time t. That looks like we plugged this into a calculator to approximate it. And the good news is we got a positive timeout. If we were to get something like a negative timeout, then something's probably gone wrong, and we want to check our work. Right? We're not running backwards in time. We should get positive times out of this. And it seems like a reasonable thing, 167 minutes, right? And note that that meets up with some other information. We know that at the 480-minute mark, there's 1 billion cells. So we shouldn't have a billion or more at the 167-minute mark. And indeed, we don't. We only have 20,000. So that's good to see. It's nice to kind of check things to make sure everything fits together when we answer a group of questions like this. So that's an example of population growth. Let's look at half-life. Okay, half-life uses the same formula. Now, they sometimes use m for mass because a lot of these things are measured in mass, but y standing for quantity is just fine. Variables are just variables. That's okay. So we have strontium-90 has a half-life of 28 days, and a sample has a mass of 50 milligrams initially. Okay, so we're going to start y of 0. Our time t equals 0, beginning of the experiment or observation. We have 50 milligrams of this stuff. It's got a half-life of 28 days, so our unit of time will now be days, right? They ask us to find a formula for the mass remaining after t days. Well, we just need to fill in y of 0 and k for this formula. So first things first, we know y of 0 right away. It's 50. So I can just pop that in right here. And now all I need to do is find k. Because k needs to be determined for this situation to be a fully ready to go model or formula. So to find k, the only thing I have to remember is that after t equals 28 days, right, y of 28, we're going to have half of the 50 milligrams we started with because it has a half-life of 28 days. Well, that leaves us with 25 milligrams after 28 days. Okay, well, this looks like when we plug this in, y of 28 is 25, and that's equal to 50 e to the k times, well, t equals 28. That's how we got this number in the first place, just like we did with the population growth model on the previous page. And now we're ready to start solving for k. Divide both sides by 50. We have 1/2 on the left. We have e to the 28k on the right. And natural log of 1/2 of both sides, and we get natural log of 1/2, and it cancels with the e on the right-hand side to get 28k. And solving for k, we just have k is equal to natural log 1/2 over 28. Oftentimes, the k value, the relative growth rate, is going to look like this, something like natural log of something divided by another number. It's just the format that's going to come out with these. So it's good to keep in mind. So to put our proper model fully together, we update this thing by putting in k's value. We have y of t is equal to 50 e to the natural log of 1/2 over 28, there's k, times t. Remember, this is a formula or a model that allows us to plug in any time t in the future, so any number of days later, since days is our unit of time in this problem, and see how much of this stuff is left. Should be decaying. Now, one thing you could check, we don't see it here, But if you took the natural log of 1/2, you would realize, well, that 1/2 is a number less than 1. And if you look at the graph of natural log, you'd remember that, well, natural log of a number that's less than 1 actually comes out to be a negative value. So this, in fact, is a negative k here, and that's good because this is a problem where something's decaying. It's decreasing over time. Okay, so anyway, find the mass remaining after 40 days. Well, that's y is the mass at the 40-day mark. Y of 40 is equal to 50 e to the, here's our k value, times t equals 40 up here. So we just pop in the number into the formula and calculate as is. 40 over 28 is 10 over 7 times natural log of 1/2 is left there. And I didn't bother to come out with that, but I think that students being careful with parentheses here would do just a fine job of figuring out how much that is. You should see that that number is less than 50. If it's not, then something's either gone wrong here or we've made a mistake further back. So then lastly, part C is how long does it take the sample to decay to a mass of 2 milligrams? Again, how long? Time t, very similar to the last question that we did on the population problem of the previous page. So to decay down to 2 milligrams, to end up with 2, right? A quantity or a y value of 2 here. And then that's equal to the right-hand side of our model, right? All of this stuff. And then we just solve for t as we've done before. Divide both sides by 50. Now we're ready to take natural log of this side and this side to cancel this e. And what we'll get is natural log of 1 over 25. And we have 1 over 28 natural log of 1/2 times t remaining on the right because the e cancel with the lower natural log. And solving for t, we have 28 times this divided by natural log of 1/2. That's exactly what we see in the box here. And again, this could be approximated as a decimal. Of course, we should see a positive time there, and I think we will. It probably takes a long time to get there, right? Or maybe it takes many days to get there, I'll say. Be careful of some things here. You see e to a natural log up here, and your temptation is to cancel that. You cannot cancel that because we have it's divided by 28, it's times the t on the outside. All these numbers here would have to be in the argument of natural log for there to be a cancellation. So you have to have this clean e to the natural log or natural log of e situation in order for that inverse cancellation to happen. So don't get too enthusiastic with log and exponential cancellations in these problems. Okay, so our last problem is actually a slightly different equation. This is Newton's law of cooling. It turns out it's more or less the same exponential equation, but it's got one little bit of a hiccup in it, and that's that this term right here is a little different. So capital T stands for temperature, lowercase t is still time, K is still the relative growth rate. Here's capital T again as the temperature, and then T sub S, this is sort of written in and corrected on my part, T sub S is the surrounding temperature. Temperature surrounding, right? Temperature of the surroundings. So that's a way to think about this. So this is a model for if we take an object and place it into a room or in a surrounding situation, surrounding medium that is a given constant temperature, then and this initial object's temperature, this object's initial temperature is different than the room, then of course eventually this object is going to change until it becomes the same temperature as the room, right? So the way to find a solution for this is a little bit more mixed up, and maybe this is even less necessary for you to be able to follow, but I'll just run through it as quickly as possible here. So what we decide to do here is let's just say y is equal to t minus t sub s. So then all this is replaced by y. And then on the left-hand side, we worry about, well, what's the derivative of that? Well, the derivative of this with respect to time, little t, well, it's just y prime. It's equal to t prime because this is a constant, right? We assume that this will be a constant in any of our problems. It's a constant surrounding temperature. Okay, so it turns out that these derivatives match. So this equation here, when we make this substitution, we're able to rewrite this whole equation as an equation we already know. Well, we know that this equation has this solution. We worked that out on the first page. So now we've got that piece of information. And if we fill in the details here, we know that this y on the left-hand side, well, that's t minus t sub s. In this case, I've added t sub s to both sides. So t sub s is over here on the right. Now, if I look at the rest of this, I have y of 0. Well, y of 0 is t of 0 minus t sub s. So there's y of 0 right here. And then I just have my e to the kt like I did before. Okay, but once this formula is in hand, which it is now, we're equipped and armed and ready to do Newton's law of cooling and heating temperature problems. We can just use this formula as we have it right here. So let's have a look at this example. So a cold drink taken from the refrigerator has a temperature of 5 degrees Celsius. After 25 minutes in a 20 degrees Celsius room, its temperature has increased to 10 degrees Celsius. Okay, so of course, we take a drink that's 5 degrees out, we put it in a 20-degree room, and the drink is going to warm up. Its temperature is going to increase over time until it more or less is equal to the room temperature. So what are we asked to do? They ask us to find what's the temperature of the drink after 50 minutes. All right, so we need to set up a model that can do that, right? Here's the thing, right? We're tempted to say, well, okay, 25 minutes, this thing went from 5 degrees to 10 degrees, so it doubled its temperature. So maybe when we go from 25 minutes to 50 minutes, maybe it's going to double its temperature again, right? Maybe it'll go from 10 degrees Celsius to 20 degrees Celsius at the 50-minute mark. Well, you shouldn't believe that it's that easy, right? Because then the other question would be this, well, maybe it doesn't do it that way. Maybe from the 25-minute mark to the 50-minute mark, it increased by 5 degrees Celsius from 5 to 10 at the 25-minute mark. So another 25 minutes, maybe it increases another 5 degrees. Maybe its finishing temperature is 15 degrees. Again, reasonable guesses, but not at all an exact answer or a good approximation of this situation. Newton's law of cooling does a fantastic job of actually helping us model this situation, especially when the room that the drink is in is much larger than the drink and stays at a relatively constant temperature. Okay, so let's get into it. So this capital T in our model, this one, is the temperature of the drink or the object that's in the surroundings. Okay, T sub S, the surrounding temperature, is the temperature of the room. That's 20 degrees. Initially, the drink is 5 degrees Celsius. So T at time 0, or T of 0, is 5. And the other piece of information we know is that the temperature at the 25th minute is 10 degrees Celsius. It has increased to 10 degrees Celsius. It's not increased by 10 degrees. That would be adding 10. It's increased to the temperature of 10 degrees Celsius. So T at 25 is 10. All right, we need this model or this formula, the temperature as a function of time. Well, the very first thing we can put down is T of 0 minus T of S, T sub S, right? So this is 5 minus 20, filling in for this T of 0 minus TS. And then also TS out here is 20. It's a little bit different than how the book does it. I just give you this formula all the way through instead of having to piece it together through Y variables. So I think this is easier to work with. So anyway, 5 minus 20 comes out to negative 15, and T sub S is just plus 20 out here. Okay, and then we just need to find K. K is our mystery here in this thing, and the way we find K is the way we always have. The information we haven't used yet is this one. At the 25th minute, the drink has cooled to, or is warmed to 10 degrees. So now I'll say 10 equals T of 25, the temperature at the 25th minute. And then for my T variable, time, I plug in 25. There's an extra step. I have to subtract this 20 from both sides. When I do, I get a negative 10 over here. And now I have negative 10 equals what was remaining on the right-hand side. Divide by negative 15, we get positive 10 over 15, e to the 25k. Now we're ready to take the natural log of both sides. We have natural log of 2/3, that's just 10 over 15, of course, equals 25k, and now we have k. So now I can plug K into my model, update the model so that it's now ready to predict for any time lowercase t. And well, the time of interest is 50 minutes. What's the temperature after 50 minutes? Well, T of 50, the temperature at 50 minutes is, well, plug in 50 for this T here. And it looks like I've rearranged it, put that 50 over the 25 times natural log 2/3, but it's all going to end up at the same value as long as we enter that into the calculator correctly. And what we should get is a value here that makes sense, right? Of course, this number should be somewhere between 5 or 10 degrees because we've gone longer than 25 minutes, and it should be less than or close to 20 degrees. It shouldn't be more than 20 degrees. It can't warm beyond it. And that's actually a really interesting fact, right? If we thought about this thing as a function with a limit, if we run t off to infinity, what does this function overall trend to? Well, we'd have to know a little bit more information about the argument of e here, right? Natural log of 2/3 is negative because 2/3 is less than 1. So this is e to a negative something times t. As t goes to infinity, well, this is e to the negative something t, right? So this whole part here is going to 0, and that's 0 plus 20 degrees. And that's what's probably the most intuitive part about all of this, is that as time goes to infinity, if we leave that drink in the 20-degree room, it converges to the temperature of 20 degrees. Of course it does. And the mathematical model here asserts that intuition. It confirms that intuition. Okay, lastly, what will its temperature be? Oh, when will its temperature be 15 degrees Celsius? Again, this is simply the inverse problem. We take our 15 degrees Celsius of the object and we write it down as the value it's going to get to, and we're asking for what t value does this occur, and all the same things happen here. Subtract 20 from both sides to get a -5 on the left, divide by -15 both sides to get 1/3 over here, natural log of both sides, and then solve for t. And again, we could also get a calculator approximation. So there it is. Now, these aren't the only applications of exponential functions, but there are a few simple ones that really kind of show what calculus is actually all about. Mathematical modeling relies very deeply on differential equations like this one and like the one on the first page, and beyond this, much more complicated differential equations than what we have here. But it's nice in Calc 1 to see just a glimpse of that, to understand that talking about rates of change and derivatives of functions with respect to time really does have a place in the physical world and in applications.